A vector is represented by an arrow, which has a head and a tail. The length of the arrow represents the vector's magnitude. So then there's some pictures to tell us this. We've got a tail and a head of the arrow. And so all vectors head from head to tail. And that we have in this different lengths. 25 meters is longer than 18 is longer than 15. So the directions are shown in brackets. For the degree measure, think unit circle. And you haven't gotten here yet in pre-cal, but what they tend to do in math class is they start in quadrant 1, and they'll spin around to quadrant 4. And so if this is 0 degrees on our positive x-axis, that would be completely east. 90 degrees then is north. 180 degrees, 180 from the source, is west, and 270 is south. 45 degrees would be exactly northeast. 135 would be northwest. 225 would be southwest, and then southeast is the last one. If an angle is listed with no direction, then the unit circle notation is assumed. So if you see 60 degrees out in the wild, it's assumed that it's 60 degrees north of east. 40 degrees, north of east. So what that means is I'm taking a east line and guiding around the circle from it. So 40 degrees can be written as 40 degrees north of east, or it can be written as 50 degrees east of north, because they're complementary. So we're really both describing this line here, okay? And so we can either count up from that line, which would be going north of the east line, or counting from this line, which is east of the north line, and really it's just how English works. So if we're going to draw these angles, we've got 30 degrees, and the complementary angle is going to be 60 degrees. So we have 30 degrees north of east, or 60 degrees east of north. 215. We have a line between 90 and 180, closer to 90, to where it's 25 degrees west of the north line, right? Because now we're in quadrant 2, we're on the west side of it, of that north line. And the complementary angle would be 90 minus 25, which is 65 degrees north of west. 260 is really close to 270, and 270 is straight down. So 260 has rotated almost all the way around. And we're going to say that it is 260 is the same as 10 degrees west of the south line, or 80 degrees south of the west line. And 335 is not too far off from 360, a full circle. We are 25 back, 5, carry the 1. Yeah, 25 back. So 25 degrees south of east, and 65 degrees east of south. Now, all of these should have arrows because they're all vectors. They all have a direction, even if they don't have an actual generalized unit with them. So To add vectors, we can start manipulating vectors. And to add vectors, we're going to choose a scale and then add our vectors head to tail. So if I were to underline things or have things that you filled in the blanks, it's add head to tail. The resultant is bold, so that could have been an underlined word or a left fill in the blank. A resultant vector is drawn from where you start to where you end. The equilibrium is the opposite of it. The resultant vector's magnitude can be determined graphically by measuring its length and converting the length using the scale chosen, or its direction is the direction that it points. And vectors can be added in any order. To subtract one vector from another, add the negative version of that vector. So we'll talk about what all these means on the next page. I'm just taking a good glance that I remember everything. So when Luis walks 10 meters north and then 5 meters west, we add them head to tail, 10 meters north and 5 meters west. If I were to go from start to finish, beginning to end in a straight line path, that would be our resultant, because it's the up and to the left that we added together. To go the opposite of the resultant, to go back home exactly from our final position, would be our equilibriant. And lastly, I could add them in any order. I could add it going to the west first, 5, and then up 10, and I'd end up in the same spot. And if they're exact numbers, I'd end up exactly in the same spot. So given all of this, we can also see that what happens when we negative or subtract. We have A, which is negative west. We have B, which is south. So when I have A minus B, I'm going to say A. And instead of going down, I've saved myself room to go up. It's still head to tail. I just flipped around the direction that this is 30 meters per second and this is 40 meters per second. So you know that the hypotenuse is probably a 3, 4, 5 triangle to 50 meters per second. And it's not crazy to have speeds. I put a tennis ball on the table and pushed it 2 different directions with meter sticks just to show that it's not just the speed of one meter stick but the other. And the ball moves down the diagonal just fine with the speed of both up and to the right typically. To move on from this, we can actually solve why that was 50 meters per second, 30, 40, 50. And you might have realized that's the 3, 4, 5 triangle. But honestly, those aren't even the right answers. It just told us to draw it, I think. It says draw a sketch. Draw a sketch, because to figure it out, the math, you need trig. And so we have Miss Gray, who walks 5 kilometers east. 1, 2, 3, 4, 5. And then 6 kilometers north. Uh-oh, I didn't save myself room. 1, 2, 3, 4, 5, 6. We know that she started here, she ended over here, and we're trying to use trig to figure out exactly where she is. So she went this path, or the equivalency of that path. And so we need to say a squared plus b squared equals c squared. And we say that if she walks 5 squared, that's 25, plus 6 squared, that's 36. We get, why can't I do this in my head? 25, 36, 61. And so we have root 61, which is less than 8, greater than 7. It's pretty close to 8. I'd say 7.8. Let's just do it. I've got a calculator right here. Square root of 61 is 7.81. 7.81 is how far she walks from beginning to end. And so I'm going to put a meters next to that. Not really beginning to end. We're not done. So here's the thing. If it asks us for the vector, we definitely need to report the direction back. And so this would be actually I like doing the inverse tangent. So tan theta is typically rise over run. That's why I say it's always the tangent whenever I'm talking about average velocity. But anyways, all that aside, we can say tangent of rise, which is 6, over run is 5, and then we get 1.2. Sorry, tan inverse of 1. So that's why we need to do the inverse tangent of 6 over 5 to give us the angle. At this point, my calculator is already in degree mode. Tan inverse. Inverse tangent of 6 divided by 5 is 50.2. 50.19 degrees on a regular graph. So that is north of east. So our full answer has two parts. We have the distance traveled with an angle of 50.19 degrees north of east. So a quick summary of what we've done. We've taken the angle